Hi everyone. So in this video we are going to find expressions that relate the critical constants of our phase diagram, so the critical volume, the critical temperature and the critical pressure, that relates these quantities to the A and B constants that are in the van der Waals gas equation. Okay, so let's write down first the van der Waals gas equation. We're going to use the molar form, so that's P is equal to RT divided by Vm minus B minus A over Vm squared. Okay, so the two constants in here are A and B, and we want to find expressions that relate A and B to Vc, Tc, and Pc. And so if you remember from our discussion in lectures, so if I draw here an isotherm of molar volume on the x-axis, pressure on the y-axis, then you remember that at our critical temperature Tc, that our isotherm kind of at high volumes looks similar to the sort of ideal gas equation isotherm, but then there's a point here where we get this inflection and then a steep increase in the pressure for further decreases in the volume. Okay, and so this inflection point here is our critical point. Okay, and so this is characterized by the critical volume, and this value of pressure we call the critical pressure. Okay, so this point is characterized by, it's on the isotherm that's at the critical temperature, and it occurs at the critical volume and the critical pressure. Okay, and so since this point is an inflection point, then we know that the first and second derivatives of the pressure with respect to the molar volume, on this isotherm, so at the critical temperature, have got to be equal to 0. Okay, so dp dvm and d squared p dvm squared at Tc are equal to 0. Okay, so what we need to do first of all is to find these derivatives. So I'm going to write down again the van der Waals gas equation, but I'm going to write it like this: RT times Vm minus B minus A Vm to the minus 2. Okay, so let's find the first derivative. So dp dvm. This is, oops, I forgot the minus 1 here. So this is going to be equal to minus RT Vm minus B to the minus 2. Then it's minus 2 times minus. We have plus 2A Vm to the minus 3. And then the second derivative of pressure with respect to molar volume. Then, so minus 2 times minus, that's plus. So 2 RT Vm minus B to the minus 3. And then minus 3 times 2, so this is minus 6A Vm to the minus 4. Okay, so that's just the first and second derivatives of the van der Waals gas equation. So we know that at the critical temperature, these are both equal to 0. So let's write that down. So, so at Tc, then we can write minus Tc divided by Vm minus B squared plus 2A over Vm cubed is equal to 0. Let's call that equation 1. And 2RT divided by Vm minus B cubed minus 6A over Vm to the 4 equal to 0. So that's equation 2. Okay, and we're going to work with this with the second term here. You can see we have this minus 6A over V, oops, that should be Vm to the power of 4, Vm to the power of 4. And in the equation 1, we have plus 2A over Vm cubed. So if we multiply equation 1 by 3 over Vm, then we'll be able to add equations 1 and 2 and cancel the second term. Right, so let's do that. So 1 times 3 over Vm gives us minus 3 RTC divided by Vm minus B all squared plus 6a over Vm to the power of 4 equals 0. And let's call this equation 3. Right, so now you can see that if we add equations 2 and 3, then we can cancel out this 6a over Vm to the power of 4 term. Okay, so 2 plus 3 then gives us 2 RT divided by Vm minus B cubed minus 3 oops, this should be TC. 3 RTC divided by Vm minus B squared is equal to 0, yeah, because the 6a over Vm to the power of 4 terms have cancelled. Okay, so let's call this one equation 4. So now if we do 4, we want to simplify this. Okay, so you can see that the RTC terms can cancel out. So, and to simplify, if we multiply by Vm times Vm minus B cubed, okay, and to cancel out the RTC terms, let's divide by RTC. That's a 4 multiplied by this is going to give us, so the first term is going to be just 2 times Vm. It's a RTC cancels, and so does the 1 over Vm minus B cubed. And then the second term is going to be, the RTC disappears again. We'll still have the 3. The Vm is going to cancel, and then we'll have Vm minus B cubed in the numerator and Vm minus B squared in the denominator. So then this will just be Vm minus B is equal to 0. And then if we expand this out, we have 2Vm minus 3 Vm plus B is equal to 0, or you can see this is minus Vm plus B is equal to 0. So this tells us that Vm, oops, I forgot the 3. This is minus 3 times minus B, so this is plus 3B. Vm is equal to 3B. Okay, and so the particular value of Vm that we have found then is this value here. So this is actually Vc. Okay, so this means that Vc is equal to 3B. Okay, so that's the first of our the first of the 3 critical constants that we were working to find. So next, we can substitute Vc back into one of these equations. Let's use equation 2, or equation 1, I guess, maybe equation 1. So minus RTC over Vm minus B all squared. So equation 1, minus minus RTC, what was it? Sorry. Minus RTC over Vm minus B squared, Vm minus B squared, and plus 2a over Vm cubed, plus 2a over Vm cubed is equal to 0. Okay, so then let's replace Vm here with Vc is equal to 3b, and then we will have minus RTC divided by, so this is 3b minus b all squared, so this will be 2b squared plus 2a over Vm cubed, so this is 3b cubed is equal to 0. Right, so what do we do? Next, minus RTC over 4b squared plus 2a over 27b cubed is equal to 0. And let's then multiply by well, let's just multiply by let's say 4b squared minus RTC plus 4 times 2 is 8. This would be 8a divided by 27b. The b squared will cancel. Is equal to 0. Okay, so that tells us then that TC will be equal to 8a over 27br. I guess, yeah, that is correct. Okay, critical temperature 8a over 27br. Yep, so that is now the second of our two critical constants. And to get PC, I think we just will substitute back into the original van der Waals equation. Yep. So let's say the van der Waals is P is equal to RT over Vm minus B minus A over Vm squared. So we're gonna, so let's add to that then these new values of TC and VC. So that will give us that P P. Okay, so we're yeah, okay, maybe I could just write this out. So this is going to be PC is equal to R TC over VC minus B plus A over VC squared. Okay, just to be a little bit more explicit about what we're doing. Okay, so then PC is equal to R times TC, and TC is 8A over 27br times 1 over VC minus B, but remember VC is just 3b. So this is just 1 divided by 2b plus A over 3b squared. Okay, so let's just simplify that a bit. R times 8a divided by 27. Hang on, let's the 2 and the 8. So let's cancel that out to make that 4a. R times 4a divided by 27b squared r plus a over 9 b squared. All right, okay, obviously the two r's can cancel, so that is going to be 4a divided by 27b squared plus a over 9b squared. Right, okay, so then if we multiply the second term by 3, yeah, okay, oops, there's also this, sorry, there's a mistake here. There's minus here, so this should be a minus, this should be a minus. So let me just fix that. Oh yeah, these should be minuses too. All right, so what we will do then is this term here, we're going to multiply that by 3 over 3. which is just 1, so then we can do that, no problem. So this is 4a divided by 27b squared minus 3a over 27b squared. And so clearly that is 4a minus 3a is a divided by 27b squared. Let's check that. Yep, and that's what we're expecting. Okay, so that gives us that the critical pressure PC is equal to a divided by 27b squared. Okay, so that's the third of the critical constants that we're looking for. So that's it. What we did here is we said we wanted to find expressions that relate the critical pressure, the critical volume, and the critical temperature that all occur here at this point. We wanted to relate those to the van der Waals constants A and B. And so in order to do that, noting that this point is an inflection point, we just found the first and the second derivatives of P with respect to Vm and solved, and in the end we get our three equations. Vc is equal to 3b, Tc is equal to 8a over 27br, and Pc is equal to a over 27b.